All right, hello to my writing class, and I think I'm going to just go ahead and post this on YouTube so anyone who wants to can watch in, and you can also refer to the timestamps and things like that, because I want my writing students to be able to come back and look at a particular technique later when they want to. Because what we have right here is we're introducing 10 major techniques, and if you can see them right there, major techniques you might come across if you're analyzing art or artifacts for chemical composition, especially what chemicals make the color that you see on the artifact. And so we've got 10 fingers, and so I give you 10 techniques, although they are related, and you'll see about a couple of them in every single paper that analyzes art. And they're organized in this sort of order. The ones you'll see more often are at the top, the ones you'll see less often are at the bottom, but you will see a lot of different things as you move through. And the framework I want to use to go through this, we're introducing the different topics and how they relate to particular papers, because this is exactly what you're going to be asked to do in the writing class, to find and look at a particular paper that uses multiple ones of these techniques to understand what's going on. So here I'm going to walk you through this particular paper. This one is interesting because it has a very clear question and hypothesis. What's wrong with this picture? The technical analysis of a known forgery. Now, one of the things I can see is that you can look at the addresses of the authors. They're from a museum of art. These are art conservators. They're academics who study art first, and the chemistry is used as a tool. I find that this is often where I can understand what's going on better than when the chemists talk about it. And so this is perfectly valid and good, but they're speaking. Notice that this is technically it's not an article, it's a chapter. It's a chapter in a book that is called the ACS Symposium Series. What this means is most of these were talks at an ACS conference, American Chemical Society conference, which they turned into a book chapter. I'm actually doing one of those right now. They turned it into a book chapter and they published it as a book. These were peer-reviewed, and these are genuine scientific literature. But the nice thing about it is there aren't the restrictions sometimes that there are in terms of space from a journal article. And so they have more time to explain things. That's why I like to use these. Writing students, something like this is a great paper for you to use, because in my opinion it's a little bit more accessible than the typical journal article. And it's peer-reviewed, and it's got data. I mean, more could you want? The question that they're asking here, one of the ways in which this is more accessible is they come right out and they tell you what their question is. They are analyzing a known forgery. This is a painting that was established as a forgery, and then they're analyzing it to say, okay, we know this is a forgery. How can we tell from analyzing it? And that could help us when we have a painting that we're not sure about. We analyze it the same way. We see the same things. We say, I think that other painting is a forgery. So this is kind of a cool test case. If you have a painting you know is a forgery, how can you tell by looking at it? Now, this is actually involved with an FBI investigation, that there were paintings, including one signed as Sarah Hahn that was dated 1866 AD, and that's a little bit weird. Why would you be putting that on if you were actually painting in 1866? Anyways, the FBI says they have evidence this was actually painted in 1985 and was given to Buffalo State College by the courts in 1991 for study and research. In this case, not study of an old painting, but study of a modern painting that was forged to look old. It's kind of cool. So how can we tell? So let's look at the painting. This is what it looks like under visible light. And, the style fits 1866. It's sort of a folk art kind of style. The colors, everything looks right, but of course it looks right. This is the front. The back side is called the verso. And so we're going to look at the back another way. But, looks right to me. That's what the forger was thinking of. The forger was not expecting chemistry to come and show that it was a forgery. Okay, so 8 of our 10 techniques are going to be are considered non-invasive, and many of these are used in this paper. I just want to say that most of these techniques, the way they are used most of the time is non-invasively, which means that you shine it on the painting or shine it through the painting, and you detect the light coming off. As long as you don't have the radiation too high, and as long as you don't burn the painting, you actually don't harm the painting. And as you can remember from our Hidden Van Gogh paper, they used XRF non-invasively to be able to detect the Naples yellow pigment that was underneath other layers of pigment. And so there's lots of acronyms as you move down this. Most of these are forms of using light. And if you can use the light in the right way, you don't damage the painting. It's non-invasive. There are other techniques that are invasive, or you can take a paint chip. By the way, most of these non-invasive techniques, you can use them invasively if you take a paint chip and then you analyze the paint chip, like a cross-section and things like that. So this is not an either-or necessarily, but in most of the cases we're going to show you, these are non-invasive techniques. A couple of the other techniques are necessarily invasive because they have to destroy at least part of the painting in order to analyze it. It can be a small part, but it's still destroyed, and that's what matters. So under UV light, we're going to turn around, look at the verso side, and what you see is something really suspicious. You see it glowing under UV light. You remember I talked about in class that there are these chemicals called whiteners, and what they do is they absorb UV light and they glow in the visible range. And this makes something glow a bit under regular sunlight with UV in it. And so they're commonly put in things that we want to be white, like fabric and like canvas, because canvas, a whiter canvas, is more preferable for most painters. Truer colors and all that. But the weird thing is, under UV light, this painting, 1866, before whiteners were invented, there it is glowing. I mean, there could be another explanation for this, but we know right now it's because it's a forgery. This is a red flag. Now remember, when you're looking at the front of a painting, you have different wavelengths of light will actually interact differently with different layers of the surface. X-rays can pass right through. Light can pass through layers and then reflect off lower layers and then pass through again. One of the reasons why oil painting is so amazingly vivid is because of what it does with the light. You can have different layers of oil that will let different wavelengths of light go through, and then they'll bounce back again. One of the things that can happen, so this happens with oil paintings, and this can be different for different wavelengths of light with oil. But one of the things that happens with infrared light, infrared has a very long wavelength, and so it's able to pass through many layers that are opaque to visible. That visible will bounce off it, but oil, will gather it and things like that. And I want you to think about it to realize that varnish is actually a layer that works like this for visible light. Varnish goes on top of the paint, visible light goes through it, and then comes back out, and you can see the paint. It's clear in the visible range. What's interesting is that infrared, because of its longer wavelength, will actually pass through the paint layers, and it will bounce off of the white layer on the behind the paint, which is called the ground layer. So when you have a painting that's like this, and many paintings are, you will have the transmitted light that will be reflecting off of the white ground, but it won't be able to reflect off of, say, the charcoal lines that are drawn on the white ground. So what you end up getting is you get a black and white photo. You're just showing where the infrared's reflecting off, but you can see the underdrawing. You can see right here, you're looking through the blue paint, and you're seeing where the artist sketched out in charcoal what they were later going to layer on in paint. So this is a really cool technique, and I talk a little bit in my book chapter about how you can even do something like this with your iPhone if you get the proper kind of IR filter for your phone. So they used this technique for it, and they showed you it reflected off the white canvas, and it showed this straight charcoal line that ran behind the house. Also, the other thing that shows up is paint cracks show up vividly in the near infrared, because of the way they reflect off the white ground, you can see the pattern of cracking no matter what the visible color, because it shows up as white in the near-infrared reflection. Why this matters is that you look at the pattern of cracking, and those cracks are really even. You compare that to a genuinely old painting, and it's cracked in some areas and not in others. It's uneven on the general painting. So over time, cracking should be more uneven. It usually starts at the corners. I don't see any difference between the corners and the center. So it looks like whatever caused the paint to crack is not the usual passing of time and aging. It may have been forced to crack by a forger's technique. The other thing that they did, so then they did an X-ray radiograph. Remember, this is like the X-ray, taking an X-ray of your hand or whatever. Where you see the calcium in the bones in your hand, you should see the lead white that was very commonly used for pretty much everything, or lead red, or maybe some other lead paints. Lead was used so much in previous paintings. You should be able to see a lot of heavy elements. They will light up with the heavy elements. But there's very little lead in this painting. You don't see anything. There should be a lot of dense metals if this was an old painting. Again, maybe the artist chose to use non-lead pigments because you could. They just didn't tend to work as well, so most artists didn't do that. All of these are red flags, and the red flags add up for this. So now we've got 3 techniques that we've gone through. So I want you to remember about X-ray fluorescence. They're going to apply that technique next. And remember that there's a whole thing where you have X-ray photons coming in. They move electrons around. Each element has distinct energy levels for their electrons. This means that the electrons coming off, they're also in the X-ray region in many cases. And the color, the wavelength of the X-rays that come off will tell you which element is there. And so this is, I've actually showed you this before. This is what they did where they did the X-ray fluorescence of a white spot. And they expect to see a lot of lead. They see very little lead in this, just a tiny bit of lead. They see a lot of titanium. And if you look at that periodic table of discovery, titanium is a 20th century element. It's very good for making white paint, and it's much less toxic than lead. So as soon as we made it, we switched to it. But somebody painting in 1980 would have easy access to titanium and difficult access to lead. It was the absolute reverse for someone painting in 1866. So this XRF spectrum is not just a red flag, it's a scarlet flag. Here's how they talk about it. Relatively weak lead signals in each spectrum are probably due to residual lead white ground left from stripping the reused canvas. This forger bought a cheap old painting and stripped the canvas, and that's why there's a little bit of lead on it. They found peaks of barium and zinc occurring together, which is used. This is also an indication that there's lithopone being used, which is a mixture of zinc and barium that was used since 1874. Now this is dated 1866. So right there, this is very suspicious. So I just want to remind you that I got this figure not from the original Van Gogh, Hidden Van Gogh portrait paper, but I got this from the review describing it, and I think the review does a better job of explaining it. I just want to remind you, you can set the detector, you can do what they did here, and they can just detect all of the elements in a single spot. Or you can scan the painting, but if you scan the painting, you have to tell it which wavelength to look for. So you tell it, you set it to one of these wavelengths, like you could set it to the titanium wavelength here, and then you could scan the whole painting to see where the titanium is. Now that's what they did with this. So this is a variation of the same technique, but it looks different when you're interpreting the data. So the other techniques, and I want to talk about how they used some of the fingerprint techniques. These are the ones that make spectra. And so what they do is they can measure specific elements, but they measure the context of each element. Because the context of each element the X-ray fluorescence is not changed by the environment, which is good if you don't want to be worried about the environment. But sometimes you're wondering, okay, I know I have lead there. Is the lead bound to oxygen or carbon? Is the lead making these kind of crystal structures or that kind of crystal structure? What is the context of the lead? And that's where you need something beyond XRF. Techniques 6 through 10 use different kinds of radiation, and they collect information about the context of the chemical. Because what they do is they collect complex shapes that then you compare the shapes to each other, and you see which shapes are most similar. These can be measuring structures of the molecules, the way they vibrate, the shapes of the arrangement of the crystals, something having to do with the bonds. And so I call these spectra like the fingerprint, because you're comparing the shapes of the spectra. And what you're doing, you're not as confident with this because it's not a yes-no thing. But if you have to be comparing the shapes, and you have to say, is shape A more like shape B, which I know is substance B, or shape C, which I know is substance C. Let me show you how it works. They did this for several things. They used Raman spectroscopy, a really cool form of spectroscopy. All you need to care about is the data. If you do Raman spectroscopy on the green paint, you get this shape. If you do Raman spectroscopy on phthalocyanine green, you get this shape. Well, that's really interesting. Those shapes look really familiar. Those fingerprints might have been made by the same green paint. The visible color is the same, but it's the same down to the Raman spectrum of it. So this is the interesting thing about PG7, this green paint, a chlorinated copper phthalocyanine complex first synthesized in 1938. It was a green paint that was not available in 1866. A high degree of correlation is observed. What they mean to say, the shapes are the same. Look at how the same peaks show up in the same place. It's not perfect. Look over here. Maybe there's a little bit less of a match over here. But that could be contextual as well. This is a pure sample. This is paint in the context of a painting. This is a pretty good match. Maybe it's not a red flag, but it's an orange flag. They did another fingerprint thing called FTIR, Fourier Transform Infrared spectroscopy, and they did it to the green paint as well. Under FTIR, the green paint looks like this curve on the top. And what the FTIR does, sometimes it can react to the binder. So they tried a linseed oil binder and a hide glue binder. The difference between these is linseed oil is more modern. It was more available in modern paints. Old paints, especially folk art in that area, would use hide glue. They made glue out of skin. Actually, we mentioned the Santero used the hide of a rabbit to make glue, make a binder. And so that's what you would do in 1866 on a farm. If you are buying it off the shelf, you would usually go for linseed oil. They look both clear to our eye, but to FTIR they have different shapes. So let's play the game. Is the green paint A shape more like the linseed oil B or the hide glue C? And you can see, especially right here, you have this big peak around 3000. That looks a lot like linseed oil. Even down here, see how you have this big peak in linseed oil that goes with this big peak in the green paint. The hide glue has a big peak, but that big peak is moved over. That shape does not match as well. It's not as conclusive, but again, that's what these fingerprint techniques are for. You need a number of them, and you need to say, oh, again, this is suspicious. And once you have like 6 or 7 suspicious things, you've basically proved your case. They did more FTIR. What they did is they actually subtracted the big peaks out, so that they were saying they subtracted the green paint from the signal that, or they did some kind of subtraction to remove these big peaks that were overwhelming everything else, because the green paint was mixed in with other paints. maybe by subtracting out the signal of the green paint, they could see a signal underneath it that is another paint in these other peaks, in this mess over here especially. See, this mess is around 1500 to 1000 on the graph. Well, let's see, they're zooming in on that part. You see, this is around 1500 to 1000 on the graph. And they subtracted out the green paint signal from they've subtracted out some of the other signals. I think they may have subtracted out the linseed oil from the green paint. This is what's left behind after you subtract out what you suspect is there. And so then this gets a little more sketchy. But they even have a hypothesis for what's left behind. They found Hansa yellow. It kind of matches. You know, you have this peak and that peak, and you know, there's a little peak right here. Maybe that matches. There's a peak here. There's sort of a correlation, but you're a lot less certain. They're very speculative about this. And why does it have this lump right here? Well, barium sulfate, which they found through another region. Remember the barium that they found on the X-ray F? Barium sulfate under FTIR makes this shape. That could be that shape right there. Hansa yellow, if indeed Hansa yellow is here, was first available in 1928. So we're kind of getting weaker evidence as we go along, but that's what they're using this for. How weak can the evidence get? This is kind of questionable, but I think they could make their case. You don't want to rest your whole case on this, but I think I can see a pattern in the big spikes that could very well be Hansa yellow. There are other techniques that are invasive. Right here, X-ray diffraction and GCMS, I believe these are always invasive. These require that the sample be destroyed. The other thing you can do is you can take a paint chip. Taking out a paint chip is automatically invasive. You could try to take it out of a place where it doesn't matter. And then you can look at it under a microscope, and you can do all the other techniques to it, like you can shine UV light on it. So they have an example of the GCMS invasive technique. Now, chemically speaking, GC gas chromatography actually has the word color inside it. It separates out different colored molecules. And then they have mass spectrometry, which is just, I'll let your chemistry teacher teach you about that. But the main thing is that you have a separation. Chromatography is a separation of colors. And you have MS, which measures their mass, their weight, how much they weigh. And so, needless to say, whatever this does, it actually works for us like a fingerprint. Because you see the shape of what comes off of the GCMS, and that has a distinct shape depending on the chemistry of what is making up that chip that you destroyed, and then you ran it through the GCMS. So they took a little scraping from the surface, and they got this GCMS fingerprint from it. Compare that to B, linseed oil, and you see that you have these peaks match, those peaks match. So the peak at 10 minutes, the peak at 12 minutes, they match. And then you also see that you have a shellac, and they found a shellac that they ran through the GCMS. They got this fingerprint, and it seems to match in the major peaks as well. At least this peak at 14 matches, the peak at 13 matches. There's a peak at 11 that doesn't match, and so you've got to realize that, okay, well, there's always going to be something that doesn't match. But overall, it looks like a pretty firm case that GCMS is picking up the linseed oil in another way, and it's also picking up the kind of shellac that they used. What they could do with GCMS is you can actually take each of these peaks as a different chemical. You can actually take that chemical and you can weigh it. And you can say, what do I think the mass of that chemical is? And you can weigh it very precisely. Many times you can actually say what chemical is in that peak. And you can see they can get it down to these things. They found glycerol, they found styrene, and they can say what these things are, what these little chemicals are actually associated with. And they found a lot of chemicals that are associated with oil, and they found one chemical that's associated with Hansa yellow, this 2-chloryl N-methylbenzamine. That is Hansa yellow. And so they found that exact structure. This strengthens their previous spectrum that they said they think that there's some Hansa yellow here. Again, 2 pieces of evidence are better than 1. So don't worry about the names of those, except by matching the name. If you can match the name, you're matching the substance. Once you take organic chemistry, you can, which I know all of you won't be, but if you do take organic chemistry, you'll be able to know what structures go with what names. But that's not something you have to do now. The last thing that they did, I believe this is the last thing, they took a paint chip from the cracked part, the craqueliture, or whatever they do it in French. I can't speak French, so I shouldn't try. But they showed, if you look at this, you see that there's UV irradiation makes this glow really brightly. And there's a modern layer that's glowing under visible light that looks like a modern brightener. So again, it shows that the layer right here, that you see this bright glowing white layer, the one that I'm showing right here. Oh, and this is the most important thing. The one on the left is under UV light. The one on the right is under visible light. And you see how you have this layer that's glowing sort of blue even under visible light. So the ground layer has a whitener in it. And that is a really strong evidence that it was made in the 20th century. You can also see the green layer, the red layer. You can see all the layers here. And you can anticipate which layer was laid down first. First the white, then the dark layer, then the green, then the red. So this painting is a very useful thing because it's something we know is a forgery, and so we're going to take it and we're going to put it we're going to see what other forged paintings we can compare it to. And so they actually said, well, maybe we can carbon date the paint in it. And that's what this paper did. This paper actually took the same painting, this should look familiar, and they took this little square of white paint which has carbonate in it. I believe it's carbonate. And they took the carbon in the paint, whatever form it is, and they carbon dated it. You don't have to worry about the exact way that carbon dating works. It's not a very common technique for art analysis, but they did do it, and the carbon dating is accurate. You know, the carbon dating shows that it's only a couple decades old. It is not 1866 era when this carbon was laid down. Okay? The carbon might be from the binder too, now that I think about it. So I should just say it's from the paint. I'm not sure if it's pigment or binder. Doesn't really matter, because whatever it is, it's new. And it shows that this can be used that way. Okay, let's see how long that's taken me. Oh, I said it was going to be 15 minutes, and it's been 27. That's pretty typical for me. But we've got the time now for you to go back and look at these in detail when you're interpreting your own spectra. So I'm going to make that available for you. All right, writing class, I'll see you next Wednesday. Anybody who's interested in these things, let me know what questions you have.